All right, let's tackle a really big engineering puzzle, one that affects pretty much everything we build. Why do things break, even when they're not supposed to? You see that label built to standard, and you think, okay, this is safe, this is reliable, but the reality? Well, it's a whole lot more complicated. Let's get into why. Okay, so here's how we're going to break this all down. First, we're going to bust the myth of what reliability really means. Then, we'll meet the hidden partners that cause failures and see how they actually work together to create this perfect storm of destruction. We'll look at some pretty shocking data that lab tests just don't catch. And finally, we'll talk about a whole new way of thinking so we can design for the real world.
You know this phrase, right? Designed according to standards. When we see it, we breathe a little easier. It feels like a promise, a stamp of approval from engineers saying, hey, we've tested this for strength, for durability, for performance. It's really meant to be a guarantee of safety.
But if these standards are so solid, we have to ask the really uncomfortable question. Because let's be honest, despite all our best efforts, despite our most trusted design codes, catastrophic failures still happen. There's clearly a huge gap between the blueprint and what happens out there in the real world.
Okay, so to really get to the heart of this problem, we need to start by busting a huge myth. And that myth is that just complying with the standard guarantees perfection. It absolutely doesn't. Failure isn't about pointing a finger at one bad part. It's a system problem.
And what's really wild is that this is not some new discovery. I mean, look at this quote. We're talking all the way back in 1943. J.O. Allman was pointing out that failure is almost never just about a bad material. He said a full 90% of the time it comes back to the design and the production, the whole system. The material itself, it's usually just the last domino to fall.
So that brings us to the real culprits, right? The forces that are working behind the scenes, the ones that the standards often overlook. Let's go ahead and meet failure's hidden partners. Okay, first up, we've got fatigue. And you can really think of this as the silent killer. It's not about one single massive hit. Nope, it's the damage from thousands or even millions of small, repeated loads. The classic example is bending a paperclip back and forth. Each bend adds a tiny, invisible bit of damage until, all of a sudden, it just snaps.
Then you've got its infamous partner, corrosion. This is basically a chemical attack that works from the outside in. I mean, just think about rust. Whether it's salt water hammering a ship's hull or just plain old humidity in the air, corrosion is literally eating away at the material, weakening its structure and creating all these little weak spots.
And our third suspect is creep. This one is slow. It's sneaky. It's this gradual deformation that happens when a material is under constant stress, especially when things get hot. A great way to picture it is a metal shelf in a hot engine room. Over years and years, even with a normal weight on it, it starts to slowly sag. That's creep in action.
Okay, now here's the absolute kicker. This is the crucial problem. Our design standards? They're actually really good at testing for each of these things, but they do it one by one, in isolation, in a clean, sterile, controlled lab. They'll do a fatigue test over here and a corrosion test over there. But that perfect lab environment has almost nothing in common with the messy, chaotic reality that components face every single day.
So what happens when these different forces actually meet out in the real world? Well, they don't politely wait their turn. They team up. And when they do, their teamwork is absolutely devastating.
See, when these things combine, the effect isn't just additive. It's not like 1 + 1 = 2. It's more like 1 + 1 = 5. It's synergistic. The damage is way, way greater than the sum of its parts. Take corrosion, for instance. It doesn't just weaken the metal. It creates all these tiny little pits on the surface. And guess what? Those pits are the perfect starting points for fatigue cracks to form, and then spread with terrifying speed.
And this is a perfect example of how one thing can set the stage for the next, creating this destructive cascade. It might start with something as simple as a little frictional heating, creating tiny microscopic cracks. Then some corrosive fluid gets in there, and suddenly the fatigue damage is speeding up with every single stress cycle. And finally, in that weakened state, stress corrosion cracking takes over, and the cracks just explode, leading to a total failure. It's a truly deadly chain reaction.
This synergy, this teamwork, this is exactly what those isolated lab tests are missing. And when we actually look at the data from real-world failures, from advanced studies, well, the numbers don't lie. They're pretty staggering.
Yep. We're talking 2 to 5 times faster. It doesn't matter what industry you look at, aerospace, offshore energy, you name it. The evidence is crystal clear. When these failure mechanisms team up, Things can fail 2, 3, even 5 times faster than any of our single mechanism tests would ever predict. It really makes you think. Those safety margins we rely on might not be nearly as safe as we believe.
And just look at the sheer scale of how badly we can get this wrong. You get some pitting from corrosion, and suddenly fatigue damage happens 3 times faster. You're in a hot environment and combine corrosion with creep fatigue, you could be looking at a component life that's 3 to 5 times shorter. And get this one. Stress corrosion plus fatigue can wipe out 73% of a material's fatigue strength. In some cases, our standards can be off by a factor of 10. 10! It's incredible.
And it's not just me saying this, researchers are being really blunt about it. They say the way these failures interact is, and I'm quoting here, not merely additive. It's something that challenges conventional assessment methods embedded in design codes. What that really means is, our old way of just adding up the different kinds of damage, it just doesn't work. It's fundamentally flawed. And there's another thing. Standards are great at looking at normal, everyday conditions. But what about rare extreme events? They often miss the huge impact these can have. I mean, think about an offshore platform. A severe storm might happen for less than 0.2% of its entire lifespan. But that tiny sliver of time can cause over half of all the fatigue damage it will ever see. That's just wild.
So, all of this points to one big conclusion. We need a whole new way of thinking about engineering. You know, if the old methods aren't cutting it, what's next? It's time to start designing for reality.
So this really forces us to change how we look at things. We just have to accept that synergy is real. The combined damage is way bigger than the sum of its parts. We have to accept that the environment isn't just a backdrop, it's a major player. And maybe most importantly, we have to start treating standards as the absolute floor, not the ceiling. They're the starting point, not the finish line. And we can't forget that the sequence of events is critical. One small bit of damage can kick off that whole cascade we talked about. When you put it all together, you realize something fundamental has to change in how we see failure itself. It's not a single moment in time. It's not an event where you can point to one cause. No, failure is a process. It's a complex, interactive story that unfolds over time, driven by that mix of design, the environment, and all the stresses of operation.
And that really leaves us with a final critical question. It's a challenge for every engineer, every designer out there. If standards are just the floor, not the ceiling, then how do we build for what's real? How do we design and create things that can actually stand up to the messy, complicated, and synergistic reality of the world?